This presentation is Talos, Openpower, and the World Beyond X86, Restoring Trust and Owner Control to General Purpose Computing. And purpose here is to highlight the critical problems that are actually inherent within the X86 architecture as implemented by its primary manufacturers. I want to generate more interest in owner-controlled computing, which I think this conference already has a significant amount of. There are many viable X86 alternatives at this point. I want to introduce a couple of those. And at the end, I do want to provide more information about the Talos system. And actually, I should have put you on the next slide. I'm sorry. So that's what we're going to cover in the presentation. Next slide, please. So what is X86 anyway? Many of you out there probably already know this, but it's actually a family of instruction set architectures. It's backwards compatible. It's derived from the original Intel 8086 way back when. For various reasons, primarily patents, anything past the 486 is currently Intel controlled. That's a mid-1990s era processor, and it's pretty much inadequate for any tasks that people want to do with general purpose computing nowadays. It still lives on to some extent in embedded systems and in other industrial applications where you can't really replace legacy applications easily. Next slide, please. So, problem with x86 is you have very little owner control of any of the current machines. Machine owners actually license the firmware from the manufacturer. I don't know if any of you have the experience of purchasing a motherboard and you pop open the box and there's actually an EULA for the firmware components inside. The era of firmware actually being provided and burned onto ROMs on the main board is long gone. Nowadays with EFI and other network-enabled firmware features, you have a need to continually update the firmware, you're licensing that firmware, and a lot of times that firmware actually is what implements anti-features, and this it impacts Libre software users especially. You have hardware and software DRM in there. That means that your Linux kernel and your Linux user space are not actually executing at the highest privilege level on the system. There are actually multiple co-processors on a typical x86 machine that are executing at a higher privilege level, and they can in fact stop your Linux kernel or your user space from accessing certain areas of the machine. One of the more interesting applications, and it's not widespread yet, but you'll see more of this in coming years, is what's called the protected audio and video path. Basically, this is a way to make sure that the host CPU never sees a video stream, never hears the audio, never actually sees the audio data, cannot manipulate it. While it's an interesting technology from a security perspective, you can see the obvious issues as with regard to overall software liberty when you have software executing at a higher level that you cannot access, cannot modify, and cannot control. To make matters worse, most of this licensed firmware on x86 cannot be replaced, ever. It's cryptographically signed. Intel, in particular, has a couple of technologies called BootGuard and the management engine. BootGuard is relatively new. It's primarily used on laptops at this point. And what BootGuard does is it prevents firmware from loading unless it is cryptographically signed by Intel. That's a stage 1 bootloader, and then by the OEM of the machine. Also needs to sign any of the components beyond that. This is all enforced by something called the management engine. It's a dedicated CPU separate from the main x86 CPUs on Intel platforms. And this management engine controls many aspects of system operation. It is responsible for releasing the main x86 cores from reset on modern systems. It implements the TPM module on Intel platforms. It is responsible for implementing PAVP and for system thermal control. And actually this ties back to some of the hardware DRM I was referring to earlier. It is partially responsible for setting all the thermal limits and stopping overclocking. AMD, which is the only other main x86 provider available at this time, implemented something similar not too long ago on the consumer platforms called the Platform Security Processor. And actually on the AMD platforms, the responsibility of the management engine is split across the Platform Security Processor and another embedded CPU. I believe the firmware hub or something along those lines. So at this point, the two main x86 providers are shipping similar technology. You cannot purchase any modern machines, aside from maybe some low-end atoms, without this technology built in. And this technology is full of anti-features and cannot ever be replaced. Next slide, please. To reiterate, this licensed firmware, to which you have no control and no ability to audit, it has full system access. It's executing in what's effectively known as ring -3. It's actually below SMM. It's a very high security and privacy risk. And additionally, it's network enabled. We have no idea what it's doing. It could be communicating with the manufacturer, it could be communicating with third parties, it becomes a remote hacking risk. We just don't know. Yeah, that level of uncertainty is not something that certain organizations would want, or individuals would want to live with. Next slide. So as I mentioned before, Intel and AMD both are extremely reticent to disclose any details on the management engine, platform security processor. You cannot independently audit this firmware. Bottom line, owner control is absent on modern x86 systems. You can never restore owner control. The x86 ISA and its modern implementations is not licensed by Intel. I need to step back for a second and say that there's some sort of deal that AMD is trying to make with another manufacturer regarding x86, but it's unknown if that's actually legal, and it's unknown what Intel's response to it is actually going to be. So for now, it's shrouded in a whole lot of legal uncertainty, and we need to wait for that to shake down. It's also possible that as part of the conditions for the transfer of technology, that any new x86 chips built using the transfer technology will include something like the ME or PSP. It's all unknown at this point. So the lack of competition means that basically no alternative performant x86 platforms will ever exist. Why is owner control important? You have many separate concerns here. One of the first is freedom, the ability to use your general purpose computer in the way you would like to use it. This goes into flexibility in that you can create new applications, you can modify the existing software on the machine to fit a particular task. These are all values that I think you all are very well acquainted with. What may not be as well known is the reliability aspect. You can actually audit your critical code paths. You can make sure that what software you're executing on that machine is stable, will remain stable into the future. You control your update process, if you need to update the machine at all, which components are actually updated. In with that, there's privacy and security. And interesting concept here, continuance. I don't know how many of you have experience with larger corporations, but a lot of times you'll have a machine set up and it's in a critical path somewhere within the corporation. And it sits there. And as technology ages, sometimes it's not cost effective to rewrite an entire business critical application on a new platform. Owner control allows you to have that machine sit in a corner for a decade, as long as you keep the hardware running, without having any licenses time out, without having a critical network security issue come up within the low-level firmware that you can't correct internally. A lot of times, you'll see this with pre-PC systems. It's actually more cost-effective to go in there and patch the defect out than it is to rewrite the entire application for a new platform. And finally, competition and multi-source capability only comes when you have owner control. If you're locked into a certain platform, there is no competition unless competitor can create the exact same compatible platform. And with X86, due to the licensing and patent constraints, that's just not possible. Next slide. So what about the other closed firmware components? I hear this one a lot. The host CPU control is most critical. You also have to control any CPUs that have equal or higher privilege level. So that includes the management engine, the platform security processor, any kind of firmware hub. To a certain extent, if a CPU even has a poor design and your GPU is an equal or higher privilege level, you have to be able to control that too. There are many host isolation mechanisms available, and this is why I mentioned poorly designed. Various platforms, X86, ARM, Power, even the old OpenSpark systems have means to isolate devices from the host CPU so that the peripherals cannot access system memory outside of the host CPU constraints. And you know these as the IOMMU, the SMMU, the TCE, DVMA. Another mechanism that can be used for access to untrusted peripherals is use a bus that can't do DMA in the first place, USB 1, USB 2. That's an option for certain low-speed interfaces. But for the most part, you want a system that can actually use an IOMMU or equivalent and can make effective use of it. And in order for that to work, the IOMMU or equivalent has to be inserted between the host CPU and the peripheral device that's untrusted. Obviously, the CPU and isolation mechanism silicon has to be trustworthy for this to work. Next slide, please. I'd like to delve into the realm of CPU microcode for a moment. This is a somewhat contentious topic within the Libre software community. It refers to two distinct components. This is traditional microcode, horizontal, vertical. This is more akin to a in some ways, more akin to an FPGA bitstream, and in some ways, it's traditional microprogramming. This is not generally Turing complete or anything that could really be used to host malware. I know that there are a few possible theoretical exploits with regard to privilege escalation. It's unknown how viable those actually are. Even on X86, you need root or firmware level access to change the microcode contents. And there are usually very few microcode releases for a particular CPU. So the actual risk for traditional microcode is fairly small. Much more concerning is the firmware for any embedded parasite CPUs on the die. And I'm specifically looking at technology like the firmware hub in AMD's SoCs, or to a certain extent, you could look at the management engine CPUs on the newest Intels as something like Parasite CPU, and that's a whole different topic. Next slide. For the on-die CPU firmware, it's no different than any other highly privileged CPU. For the most part, especially on X86, that firmware has full system access to RAM, storage, peripherals, you name it. It has the resources to execute malware. It's written in a very high-level language, and it's a high risk. So you just need to separate the two areas of microcode, and I'll go more into this in a moment. Next slide, please. This is a general risk chart that was put together for internal use here. And I'd like to point out that at the high risk end, I don't know how clear it is on your screen, but you have the management engine, the platform security processor, SMM firmware, IO hub firmware, any on-die system power management firmware. These typically have full system access by design. They're closed, a lot of times they're signed, they can't be replaced. At similar risk would be any binary executables in ring 0. This is somewhat overlooked when you're looking at firmware, but the listed firmware blobs at the top of that high-risk area are lower than ring 0. Obviously, any binaries running in ring 0 are fairly high risk as well. And just below that would be any peripheral firmware if you don't have an IOMMU on your system. And that's because the peripheral CPU could access all system memory and theoretically peripherals via DMA. So the IOMMU is critical for ensuring security. In the moderate risk category, you have what I'm referring to as poorly known or system model specific CPU microcode. Essentially, there's safety in numbers. If you have a microcode release that's widely distributed, is included in multiple products for which vendors have legal responsibility, it is highly unlikely that there is malicious code or malicious switches embedded in that microcode. If you're looking at a single microcode release that doesn't match anything else really available online and seems to require for your system to work, there is some warning flags that get sent up from that. And in the low risk category would be peripheral firmware. If you do have an IOMMU, it would take a defect within the IOMMU or other side channel attack to actually make that firmware, to allow that firmware hostile access to the system. And also in low risk, I'm putting any well-known or widely embedded microcode, just because the legal risks at that point become so high to entities that are embedding the microcode that it's not worth tampering with, especially when you have multiple other avenues available for selective targeting. Next slide. So what can be done to move away from X86? I mean, the obvious answer is use a different ISA. Most Libre software users can do this. The X86 inertia stems mainly from proprietary lock-in and the feeling of convenience that comes from using what you've always used. There are many non-X86 ISAs to choose from. We have ARM, MIPS, Power, RISC. Out of those, next slide. Out of those, ARM and Power are really the main focus here. The ISA alone rarely dictates the performance limits. Where you're getting general performance characteristics are from the fact that each ISA is targeted at a specific market for the most part. And each manufacturer of the CPU issues reference designs, even ARM issues blocks and example ways to connect everything. And those designs are what typically end up setting the performance for the family. Something that people often forget, developing processors actually costs money, costs a lot of money. The ISA creator and the CPU manufacturer both need to fund R&D. X86 and the T2 are at two opposite ends of the spectrum in openness in some regards. X86 being very closed, unable to be licensed. T2 was thrown out there as a GPL project when it became obvious that Spark could no longer monetize a particular design. And in general, you want to stay away from the outliers, at least in the early phases. Long-term continuance becomes a concern. Long-term manufacturer support, especially when you're talking about general purpose computing and Moore's law still being active even to a degree, that long-term manufacturer support for the instruction set architecture is vital. Next slide. Should probably cover market segmentation. X86, especially consumer X86, is positioned in a very unprofitable region. It requires very high sales volume to even turn a profit on consumer devices. And to that end, we've been seeing a push to not only sell silicon, but also license software. There's a symbiotic relationship between a locked ISA and software developed for the locked ISA. And we're seeing a lot of software lock in or move to the general rental model, driving repeat sales or just the plain old profits off of the rental software. The laptop market is probably the most affected out of any of these markets. There are no challengers apparent at the moment on the mid to high end for laptops. There is some presence for ARM on low end laptops, but they're crippled. There are not a lot of options out there. The majority of the ARM laptops available are from devices such as Chromebook or Apple. Might be entering that market at some point. It's all up in the air at the moment. The main competitors to X86 are positioned very differently. Next slide. Put together this quick graph showing theoretical integer performance over cost. And I'd like to point out a couple things. The red circle there is where power is positioned, specifically Openpower. And the green circle on the left is where ARM is currently positioned, ARM 32 bits. That blue oval with a cluster of blue squares, that is your typical consumer x86 market. And you'll notice the number of offerings really in that region and how tightly clustered they are. Off on the right-hand side of the graph are a lot of the Xeon offerings. And I'm not completely convinced of the veracity of the theoretical performance for those numbers, but for this quick market segmentation graph, does a fairly good job in showing that the competitors are not attacking the low-end consumer x86 market. They're going for something completely different for the most part. Next slide. So when choosing an ISA, it's a good idea to avoid vendor lock-in. You want to choose something licensable. If you can, make sure that either the license you can obtain allows modification, or that you can obtain a license that allows modification if you needed to spend custom silicon. You need to verify suitability for general purpose computing for the reference designs. ISAs linked to cheap CPUs can perform very poorly, and that's all implementation detail for the most part. But like I mentioned before, each ISA is targeted this specific market, so it's unlikely that the R&D went into the reference designs to enable a low-end CPU to suddenly outperform a high-end CPU. Many of the cheap CPUs use a limited cache hierarchy and trim features needed for general-purpose computing. Something else to be aware of, especially this is prevalent on the ARM side of things, some CPUs still require assigned firmware. Just because it's licensable does not mean that a manufacturer has not locked down their specific SoC. And I'd like to put out a warning on the A1200 from AMD. It's an ARM core, but has a PSP assigned firmware, for instance. Next slide. So the two architectures that are most viable at this phase are ARM and Power. ARM is very popular, very diverse. Overall, it suffers from relatively poor design decisions from the perspective of general purpose computing. These cores have been under strong pressure to perform well in terms of power use at the minimum computational level needed to make mobile devices possible. They're very cheap and they're pretty slow. Power is extremely fast. It can and does compete with high-end x86. It's feature-rich, but it's very expensive. Furthermore, Openpower is a relatively new initiative, and it's not yet quite as diverse as ARM. We're looking at a couple of manufacturers coming online at this point. Openpower has only been available for a couple of years. Next slide. ARM has a couple of issues. The mid-range, as seems to be the case throughout these architectures, is locked. It is Libre capable on the high and low ends. At the high end, you have MXP offering various NPUs. These are full-featured systems. They have PCIe, ECC, SATA, USB 3. They can use hypervisors. They have SMP. They have an odd cache structure. It's a holdover from the general ARM design. There's no L3. The SMP structure is a little bit odd. This all limits, to some extent, general purpose computing performance, specifically in the single thread end. And to be quite honest, they're expensive compared to a typical consumer x86 offering with similar specifications. These are much more expensive machines. At the low end, you have various SoCs by Rockchip, Allwinner. Allwinner, you all know, is the GPL violator. And they don't have PCIe, they don't have ECC, they don't have SATA. A lot of times they've locked out hypervisor support. You have horrible I/O options, but they get the job done for a very low end, like a tablet or a laptop. The SoC support tends to be SPI and U-boot or Linux. Unfortunately, there's very little manufacturer support on many of this stuff. The manufacturers on the low end tend to fork Linux at a certain point and throw in their patches and say, here you go. There's very little effort to upstream any of those changes. Next slide. ARM was the first non-x86 architecture in past couple decades to really gain traction. It leverages the typical weaknesses of x86. It has a simpler design, which uses less silicon, less power for mobile tasks. You can customize those SoCs. You have a strong multi-source presence using similar features across the vendors. And I mention that in particular because some architectures, while you can purchase CPUs that adhere to that architecture, there's such a wide performance gulf or some other gulf in feature set that you get locked into one vendor. ARM, for the most part, is not like that. ARM is obviously licensable, targets mobile and network markets. Something of interest with regard to the microcode discussion earlier. ARM has a hardwired microsequencer. There literally is no microcode. It's not even a ROM. It is hardwired using logic gates. And that particular design decision does not appear to be changing in the future. Next slide. We have an example of an owner-controllable ARM64 system, and that's the NXP LS2085A NPU. This is fairly comparable to a desktop machine, modern desktop machine in some ways. There are 8 A57 cores. It takes standard DDR4 DIMMs, has ECC, you get the SMMU, which is the equivalent to the IOMMU on x86, PCIe. A couple of drawbacks. Obviously on ARM, as I mentioned before, there's no L3 cache. This particular board uses an odd form factor. It kind of looks like BTX. It doesn't actually state that it's BTX. Not sure. Worst part is that the DPAA2, which is the networking portion of the chip, requires proprietary firmware. Now you can remove that firmware, but you disable all 8 of the integrated NICs. So it might make an interesting general purpose platform if you can live with that limitation. Unfortunately, the DPAA2 component is not isolated by the SMMU, so you can't really safely use it with the proprietary firmware unless you trust the proprietary firmware implicitly. Next slide. Here's a picture of the NPU for reference. There are actually 2 PCIe slots, but one of them is obscured by that add-on network card there on the right-hand side. We're not talking a low-power machine here. That SoC has a TDP of 40 watts, and there are other components on this board that also consume power, which puts it in roughly a similar class to some of the low-end or mid-range x86 offerings for desktop systems. It's a fairly interesting board if you can put up with the odd form factor. Next slide. I'd like to move on to power. This is the main focus of the remainder of the presentation. It's the only Libre-capable core that's on par with mid and high-end x86. The low and mid-range of Openpower are Libre-capable. The high-end is still locked. I should clarify what high-end means in this context. It's mainly aimed at ultra-high reliability use. We're talking literally redundant cores that can be switched in and out online. x86 servers in any performance class do not offer similar capabilities to these machines. These are typically associated with the mainframe level of reliability levels. The raw performance of the high end is actually comparable to Openpower. The reason it's considered higher end is all due to the reliability and licensing abilities. Next slide. Power traces its roots back all the way back to the RS6000. This is an old IBM CPU back from the 80s. And it's been under continuous development ever since, all the way through Power 8 and Power 9 is well underway, or taking that out actually. It has multiple firmware components and multiple on-die CPUs. The main difference here is, unlike x86, and the source for these firmware components are all available, and they can be modified, and they can be uploaded to real hardware. Nothing is cryptographically locked. It does have traditional microcode. Unlike x86, this microcode can actually be read back out and verified. On x86, a lot of times, unless the manufacturer has distributed a microcode update, you really have no idea what the contents of that masked ROM that contains the internal microcode are. You have no idea if it contains a flaw. And so one of the interesting things about Power is they can actually read that microcode out. You can actually hash it and verify it, make sure that you are willing to trust that particular CPU and microcode revision combined. Microcode is not lost on power off or reset, again, unlike X86. This is actually stored in non-volatile memory that's externally programmed. The microcode update mechanism can be locked in hardware so that you cannot update it. This might be of use for secure systems. Next slide. Power had historically big endian. Power 7 started to introduce to certain partners the concept of little endian support, but it was not hardware-based. It was microcoded. As of Power 8, the hardware itself has little endian support. And the reason that this is important is it allows non-endian aware code to function correctly. And even within the Libre software community, a lot of people don't have access to big endian machines, and a lot of people make assumptions about the endianness of the machine in relation to a peripheral, a device, even file storage. So having little endian support in hardware eases the overall porting burden. It eliminates a lot of the odd bugs that can and do arise from large, essentially crowdsourced projects that may have people working on them that are not familiar with the concept of endianness. And that goes for large corporations as well. Power 8 specifically is actually bi-endian capable. The kernel is what sets the endianness at early boot. The bare metal firmware itself can either boot big endian or little endian kernels. And another interesting point here is that under KVM, virtual machine kernels can actually select whichever endianness they want. The hardware is capable of switching back and forth within the virtualized arena. Next slide. So right now, Openpower is comprised of the Power 8, it's called Turismo Core. I'm probably mispronouncing that. It's a single chip module. It has up to 12 chiplets. Each chiplet is actually the CPU core, L1, L2, and a shareable L3 cache. One of the unique features of Power 8, is its expansive cache hierarchy. You actually have an L3 and an L4 cache. That L4 cache is off-die. IBM does leverage EDRAM to allow these large caches to exist. We're looking at, if I remember right, 8 megs L3, 16 megs per centaur of EDRAM. So all of this combined, it's a very wide core. There's a very large die size, a relatively high TDP in absolute terms. When you actually look at the performance of the core, the TDP is very much in line with similar CPUs. Next slide. And this graph illustrates that. This is a chart of the theoretical integer performance over TDP. And those red dots at the top are actually the Power devices. If anything, the theoretical performance of Power is slightly higher than X86 at a given power level. Next slide. So Power has extremely high bandwidth. It has higher memory rewrite bandwidth than many of the X86 systems available right now. That might be changing this year with the introduction of the Haswell EP, if I'm remembering correctly. But at the moment, Power is unmatched with read-write bandwidth. It has higher I/O bandwidth than most offerings. It has a couple of unique features: a low latency coherent application or accelerator processor interface for accelerators. And this CAPI is actually a standardized interface that you can plug an accelerator system into, and you get much lower latency, higher bandwidth than you would over traditional PCIe. Power does outperform most, if not all, competing owner-controllable machines in terms of overall bandwidth capacity. This is one of its primary selling points. And depending on your application, people have seen 2.5 times performance increase over similarly specified x86 systems when their applications are I/O bound. Next slide. Yeah, to illustrate this point, we actually took some measurements internally of one of the last owner-controllable x86 machines, the Opteron 6328. I need to qualify that the 6328 and actually the Opteron series in general are relatively poor performers compared to Intel's offerings of the same time period, but those offerings were locked. So this is the highest performance owner-controllable x86 machine you can buy. And what you're looking at is the memory bandwidth over chunk size. So basically, we're transferring a certain amount of data in either stream format or random format to and from main memory, and allowing the caches to take over and supply the data out of cache if at all possible. And what you'll see is that when you start looking at chunk sizes much over 32 kilobytes or so, the memory system performance drops off rapidly. As you start to go off toward the right-hand side of the graph, that's 1 gig transfers, you're hitting DRAM exclusively, and that is the native performance of typical DDR3 DIMM. On the next slide is the Power 8 system. You'll notice a fairly major difference there. All the way out to 32 megabytes or so, you have very high transfer rates. This is all of that cache structure coming into play, including the L4 cache out there at the right-hand side. Additionally, the actual RAM to performance out to the DIMMs appears to be greater than the x86 Opteron memory controller. So this illustrates the massive improvement in memory bandwidth of Power over the older Opteron devices. Next slide. One of the interesting things about Power, especially Openpower, there is significant investment by IBM in the Linux ecosystem, as well as IBM's partners. The Openpower Foundation is comprised of, I think at last count it was near 100 individual members. Raptor Engineering is actually a member of the foundation as well, and we're all working toward increasing the amount of software and hardware available for Power systems. At the moment, Debian archive coverage is over 95%. That's actually outstripping some of the ARM offerings. It has full KVM support, including TCE. There's an unprecedented level of firmware access. No regions on the Power 8 device are cryptographically locked by hardware. And that's going to continue for Power 9 and actually into the foreseeable future. The whole point of Openpower is to keep the system open and available for people to innovate in ways that IBM may not have actually thought of. Even the LCC firmware is open source. This is the rough equivalent to the management engine system control components. And you can actually get in there and re-enable overclocking if you want to. The hardware is theoretically capable of the Chrome OS security model. So if you are concerned about securing the system, you can write a key store into Flash, set that partition read-only, and authenticate each portion of the boot process, including the use of a TPM. The main difference here is that it's your key store, or your organization's key store. It isn't a third party. You are not reliant on a third party having a master key. It's your master key that's in Flash. And it's one of the main advantages of the Chrome OS security model, which at the moment is only really effective on ARM. I know that there's an implementation for x86, but Intel owns the master keys in that case. So this keeps the full control in the hands of the machine owner, which is a major plus. Next slide. Power has good hardware support. The little Endianness mode means that most of the open drivers work right out of the box. Obviously, any closed drivers must be recompiled by the vendor, but when we're talking Linux, you're only talking a handful of closed drivers. And in particular, NVIDIA is recompiling their drivers for Power. Power chips use industry standard high-speed interfaces, PCI Express, USB 3. Actually, technically, the Power chip itself provides PCIe 3 lanes, and a lot of times the Power machine implementers bring some of those down to USB 3. It also includes some special purpose interfaces, such as capping. There's NVLink as well, but that's Power 8 Plus and above, and not really of interest to Libre software advocates for a number of reasons. In practice, most hardware works without hassle. There's very little difference between x86 and Power in this regard. Unlike ARM, the SoCs can be NES body driver support and be a general pain to work with, but Power is much more like x86 in this regard. You plug in something, it works. Next slide. So on the software side, we had extensive support for open Linux applications. There's actually some support for closed Linux applications. IBM compiled Java, the IBM Java distribution for Power. NVIDIA and NVIDIA CUDA are available on Power because of NVIDIA's partnership with IBM. There are a few notable exceptions. Chrome are not available. There's an interesting thread where Google expresses lack of interest in even supporting a community port for Chromium to Power, but that is as of 2014. In 2015, V8 was ported to Power, so at this point, it's possible that the topic of a native Chromium port needs to be brought back up, and that it might actually go through. Flash obviously is not supported. It's becoming largely irrelevant on the web and as a whole. Certain applications like VirtualBox are x86 only, but they have replacements. Use KVM and QEMU. They work great. Next slide.
We have about 5 minutes.
All right. I'm going to have to rush along here anyway. But we've actually verified some 3D support on Power Machine here. A lot of tools work right out of the box. There's no real difference no perceivable difference from x86 when you're using the machine. Next slide. Future direction, next revision will be Power 9. That won't be out before late 2017, and that's if we're not looking at any unexpected delay. It'll be a new socket, different RAM architecture. The nice thing is it'll be even more open than Power 8. They're looking to completely open the microcode and this tool chain. In general, adopting the open Power 8 systems now helps to ensure that Power 9 will remain open in the future. I know that there's some commitment to keeping Power 9 open anyway, but there's also pricing to consider, and if there's a strong adoption of Power 8, that will help bring the pricing on Power 9 systems down in the future, especially owner-controlled ones. Next slide. I'm going to skip over this particular section. You can read this on your own leisure if you want. There's a brief overview of the firmware components within the Power system. Next slide. We do have a coreboot port to Power in progress. It has stalled to a certain extent due to lack of developer time. We do have the tool chain ready, and the boot block is ready to basically have the next stage loaders written and enabled. Needs attention, needs more developers. Part of the complication here is that Power 8 starts in big endian mode, so coreboot traditionally has not had a big endian mode that's been well supported, and we're needing to go back and fix up some things, for instance, in CDFS before everything is possible. Next slide, please. There are a few closed components on Power 8. The microcode, including what's called the self-boot engine, is closed. It's not cryptographically signed. We're talking traditional microcode here. It's not cryptographically checked by hardware, so it is theoretically possible to replace if someone actually wanted to go through and try to figure out, reverse engineer, figure out how it works, and try to replace it.